All right, let's just jump right in. Ever stop to think about what keeps a rocket flying perfectly straight? Or how your thermostat nails that perfect temperature? Or how your car just stays at a steady speed on the highway? Well, it's not magic. It's something called feedback control. And you can think of it as this invisible intelligence that keeps our world orderly and predictable. And today, we're going to pull back the curtain on the most powerful and common form of it, the PID controller.
But before we get to the solution, we've got to understand the problem, right? So picture this. You set your car's cruise control to, say, 65 miles an hour on a perfectly flat road. Piece of cake. But what happens the second you hit a big hill? A simple, kind of dumb system might not react fast enough, and you'll start slowing down. Or what if a sudden strong headwind kicks up? Same deal. See, the thing about simple machines is they're awesome at doing the same thing over and over again. But they are just awful at handling surprises, what engineers call disturbances.
And this right here is basically what that looks like. This is what's known as an open-loop system. You've got your input, let's call it the amount of gas going to the engine, and that creates an output, which is your car's speed. Simple enough. But see that arrow labeled disturbance coming in from the top? That's the hill. That's the wind. That's anything you didn't plan for. And because the system has literally no way to see what its own output is doing, it's completely blind to that disturbance. It has no way to correct itself.
So that's the problem. How do we make the system smarter? Well, we have to give it a way to see what it's doing so we can actually react to these changes. In other words, we need to close the loop.
And boom, this diagram shows the solution perfectly. We've added a feedback path. Let's just follow the information for a sec. The process output, our car's speed, gets measured. That measurement then loops all the way back to a comparator, which checks it against our goal, our set point of 65 miles per hour. The difference between where we are and where we want to be, that's the error. And that error signal is what gets fed to the controller, which then adjusts the input. The system is now watching itself. It's constantly self-correcting. Game changer.
Okay, so every single control loop, no matter what it's for, is basically made up of these four key players. First, you've got the process. That's the thing you're actually trying to control, like a furnace. Then there's the measuring device. You can think of this as the sensor. It's the system's eyes, like a thermometer. Third is the controller. This is the brain of the whole operation. It figures out what to do. And last but not least, the final control element. This is the muscle. It's the part that physically carries out the brain's orders, like the gas valve on that furnace.
All right, so we've built our loop. Now let's really zero in on the most interesting part, the brain, the controller itself. What's the simplest, most intuitive way we could program this brain to behave? Well, that would be something called proportional control.
And the idea here is honestly incredibly simple. The controller's reaction is directly proportional to how far off you are from your target. That's it. So, a tiny little error gets a tiny little corrective push. A huge error, well, that gets a huge corrective push.
It really just boils down to this. The bigger the error, the bigger the reaction. Let's go back to our cruise control. If you're just 1 mile per hour below your target, the controller adds just a tiny bit of gas. But if a massive hill suddenly slows you down by 10 miles per hour, it slams on the accelerator. It just makes sense, right?
But, and there's always a but, isn't there? P-control has one major fundamental flaw. Now, don't get bogged down by all the numbers on this chart. Just focus on two things, the solid line and the dotted line. That dotted line, that's our target. The solid line is what our car is actually doing. And do you see it? See how it gets super, super close, but it never quite touches the target? That permanent gap right there, that's the problem.
And that gap, it actually has a name. It's called offset. It's a persistent, steady-state error, and it is the single biggest Achilles heel of using only proportional control. I mean, think about it for a second. For the controller to keep applying a correction, there has to be an error, right? If the error ever actually hit zero, the controller's output would also go to zero, and the system would just immediately start to fall behind again. It's a catch-22.
Now, you might be thinking, well, just make the controller more aggressive. Crank it up. And, you can do that. By making it more sensitive, engineers call this increasing the gain, you can definitely shrink that offset. But you just end up trading one problem for another. A super-sensitive controller tends to overreact, causing the system to wildly overshoot the target and then oscillate back and forth, kind of like a really shaky, nervous driver. So no, we need a much smarter strategy.
And this is where we start to get really smart. To get rid of that annoying offset for good and to calm down those wild oscillations, we need to give our controller two brand new abilities, a memory of the past and a way to predict the future.
Okay, first up, let's give it a memory. This is called integral control, and it's the I in PID. Now, instead of only looking at the error that's happening right this second, it starts to look at the total accumulated error over time. So, as long as there's any error at all, no matter how tiny, that integral action just keeps adding it up, like a running tab. This forces the controller to push harder and harder and harder over time until that stubborn offset is completely wiped out. It literally will not rest until the error is 0.
So really, you can think of it like this. Integral action is the silver bullet for that whole offset problem we were just talking about. By adding this memory of past errors, we absolutely guarantee that the system will eventually settle precisely on its target. No more gap, problem solved.
All right, next up, let's give our controller a crystal ball. This is derivative control, the D. Now, this part of the controller doesn't care about the error right now. It doesn't care about past errors. The only thing it cares about is the rate of change of the error. How fast is the error growing or shrinking? Think about how you drive. When you're approaching a red light, you don't wait until you're right at the line to slam on the brakes, right? You anticipate it. That's what the D action does. If it sees that the error is closing in really fast, it starts to back off the gas early, preventing that wild overshoot and giving you a much, much smoother ride.
And this table just lays it all out so perfectly. Proportional, the P, is your reflex. It's all about reacting to the present error. Integral, the I, is your memory. It's about correcting for lingering mistakes from the past. And derivative, the D, that's your intuition. It's your prediction of what's coming next. Present, past, and future.
So now, let's put it all together. When we combine these three totally distinct ways of thinking, reacting to the present, remembering the past, and predicting the future, we create the absolute gold standard of feedback systems, the PID controller.
You see, a PID controller is so incredibly powerful because it finds this perfect balance. It reacts fast to new problems thanks to the proportional action, it totally eliminates any permanent error thanks to the integral action, and it avoids overshooting and settles down nice and smooth thanks to the derivative action. This combination is exactly why it's the absolute workhorse of modern automation.
And this one graph, this graph tells the entire story. Let's just walk through it. That no control line way up top, it barely even tries. Then you have proportional control. It gets closer, but you can see that permanent gap, that offset we talked about. Now watch what happens when we add the integral action. That's the PI curve. It hits the target, but look, it overshoots and then kind of bounces around a bit. And finally, look at that PID line. That is the ideal response. It's fast, it's stable, and it is dead on target. That's the power of putting all three together.
So, what's the big takeaway from all this? It's that each part plays a super important but ultimately incomplete role. P is all about speed, I is all about accuracy, and D is all about stability. On their own, each one has a flaw. But when you put them together in a well-tuned PID controller, you get a system that's fast, accurate, and incredibly robust. And that is pretty much the ideal for any automated process you can think of. And that kind of leaves us with one final thought. PID control is absolutely brilliant at locking onto a fixed target in a system that's pretty predictable. But what happens when the target is always moving, or when the system itself is constantly changing? How do you control for, thousands of variables all at once? Well, that is the next great challenge. That's the frontier that's pushing us into the incredible world of adaptive control, machine learning, and AI.